everyone. I'm Marc, a postdoctoral researcher at EPFL-IKEO, and I present joint work with Jamila Mifdal and Raquel Carmo from the ESA Lab and supported by master student Lara Pasero. The work I present is about the detection of marine debris with Sentinel-2. Marine litter is a permanent pollutant in our ecosystems. Plastic bottles and other macro debris are washed into the oceans by rivers every day. They decompose into microlitter and enter the food chain. Microplastics are ubiquitous in everyday life and have been detected in human stool and even human placentas. Removing microplastics from the environment is difficult. However, macroplastics can be gathered on ocean surfaces by dedicated ships. These ship-based collection efforts should be guided by remote sensing information, but surprisingly little research is available in this regard. While a single plastic bottle is impossible to detect with a medium-resolution satellite sensor, such as Sentinel-2 or PlanetScope, aggregations of marine litter can be seen from space with these satellites. Oceanic processes that are driven by wind and ocean currents aggregate floating debris into long lines that can stretch several kilometers and can be collected efficiently by ships. These aggregated debris typically consist of different materials and can contain macrolitter. In this work, we build a segmentation model for the detection of generic floating debris. We find that surprisingly little research is present on the detection of floating marine debris from satellite imagery, which is crucial for efficient collection programs down the line. We publish a hand-annotated dataset alongside pre-training segmentation models, which can serve as a baseline for future methods tackling this problem. For this, we hand-labeled 26 Sentinel-2 scenes with 3,378 lines, where floating marine debris was visible in the satellite imagery. The annotated lines roughly outline the marine debris visible in the images, but do not always accurately reflect the extent, as the boundary of marine debris is difficult to define. In terms of the model, we trained a standard unit segmentation model with 12 input channels and a single output dimension. The loss function is binary cross-entropy. We trained the model on different geographic regions and multiple cross-validation folds. As you can see, the segmentation model produces reasonable predictions from these annotations. A challenge associated with this dataset is the diversity of objects. Marine debris are heterogeneous in nature, and the composition can vary substantially between dates and regions. In this example, we can see several patches of liquid pollutants visible in the oceans off the coast of Accra in Ghana. These patches float between ships and are likely of human origins. On the other side of the spectrum, several regions in the dataset contain floating patches of natural origin. Here we see an algae bloom captured near Rio de Janeiro in Brazil. In both cases, the model predicted the shape of the objects accurately. Still, several limitations need to be addressed. We find that some combinations of regional training and test splits do not lead to deep learning models that converge to a good solution. In these cases, simple pixel-wise classifiers, such as random forest or a naive Bayes classifier on a set of hand-defined features, namely the floating debris index and NDVI, lead to better results. The root cause is the distribution shift between geographic regions caused by the heterogeneity of the captured debris. This leads to some combination of training regions that are not representative of the remaining test regions. A second limitation of this model is a series of systematic false positive predictions on ships, coastline, and partly on clouds visible in the images is shown on the right. A more targeted training scheme that explicitly identifies and labels these objects as negatives may help alleviate this issue. In ongoing and future work, we focus on the former limitation of variability between regions. First, we aim to semi-automatically refine the hand annotations to help the model to find a solution that reflects our intuition of floating marine debris more accurately. Second, we aim to employ model-agnostic meta-learning to obtain a detection model for each region individually with few annotated samples. We find experimentally that these specialized models are able to capture the region-specific nuances more accurately at the cost of requiring few annotated samples per Sentinel-2 scene. Overall, we aim with this work to encourage remote sensing specialists to tackle this problem and improve the automated detection of marine debris in a systematic manner. We provide the dataset and pre-trained models and invite everyone to read the associated papers and clone, fork, and star our repository. Thank you very much for watching this video, and I hope to see you in the conference.